Yesterday workout. Anything did or not? Somewhat why? Went get. Oh, late went. Which time you reached? Oh, that is late where? Soon only. Here after what? After that slept. Food taken and slept. Morning which time wake up? 7 o'clock. Good. Later finish. Don't keep till next batch. Some students are keeping till next batch. Keeping, no? He is doing now this batch. Tomorrow integral class will happen. Okay, college leave have no. I think I'm thinking I will tell to start from 1 o'clock. Oh? Your college time? 1 o'clock. College time. Finishing or okay, at least online join. Okay, online join, at least notes properly write. Okay. You can take next batch also class, no any problem. Not for you, only jam student. Okay. Okay, external direct product, whatever concept I gave, that only concept. Hereafter, in this same chapter, new group, we will see UN group. Same chapter, only external direct product. This group, another name is unit group. Why unit group name? Later we will see. Another reason for unit group name. Definition will be U of n will contain any elements, but that elements between 1 to n only, and that elements with n relatively prime element. Okay, means U of n will contain relatively prime elements with n. Okay, and operation will be same multiplication modulo n. Same type one group I gave definition on starting. Remember have another one group first day. Check in notes. You at least remember. See notes, first day notes. Like that definition, any group I gave. After Zn group, see after Zn group, Zn star. Zn star group C. Not reading, only reading here. Both groups are same definition. UN group tail or Zn star group tail, both are same. Everything same, operation same also, definition same also. Zn star, I told that time Zn star, by Zn star we can't get more concepts and all, but by UN group, more concepts are. So whenever Zn star they will ask, you come in UN because both are same, and by UN group you find all concepts and you can tell about Zn star. So already we saw Zn star is abelian group, correct? So we can write here also UN group for all n belongs to natural number is an abelian group of order relatively prime element containing. So relatively prime elements notation is phi of n. So order will be phi of n. Understanding? So this is abelian group always. Sometimes cyclic group also will happen. So when cyclic will happen, when abelian group will happen, we will see everything. You write first this. We will see some examples and we will see that when cyclic group, when abelian group, both. Every time all are not cyclic. Non-cyclic also possibility. Suppose u of 10 we will see. 1379 operation multiplication modulo 10. Relatively prime element 1379 with 10. Okay. Hereafter U10 is abelian group already we know. If we want, we can go by Kelly table and we can verify also. Inverse element, everything we can find. So we will go Kelly table no need because we know we know this is abelian group. Already we did by Z10 star and all. You need, you can practice like that. If you want, we can go with direct inverse everything. One will be the multiplicative identity. Three inverse what will come? 7. 3 into 7, 21, modulo 10, 1. So 3 inverse 7, 7 inverse 3. 9 inverse itself will come, 9. 9 into 9, 81 modulo 10, 1. So 9 inverse is 9. Okay. Commutative law also will satisfy. So this is abelian group, no any problem. For all a comma b belongs to u of 10, ab is equal to ba will come under multiplication modulo 10. So here we can go u10 is an abelian group of order 5 of 10, and 5 of 10 means total elements is 4. So this is now abelian group. Hereafter we will verify cyclic or not. Cyclic means we need 4 order element, then only generator will come. So we will find order of element. So 1 is the multiplicative identity, so order of 1 will be 1. 3 we can see 3 power 1, 3 power 2, 3 power 3, 27, modulo 10, 7, 3 power 4, 81, modulo 10, 1. So 3 is the generator. Order of 3 is 4. When this is a abelian group and 4 order element existing, group cardinality also 4 means that must be a generator. And 3 inverse is a 4, no? Sorry, 3 inverse is 7. So 7 also will be the generator. Order of 7 also will be 4. So we can write that u of 10 generated by 3 and generated by 7. So finally u of 10 is a cyclic group of order 4. So u of 10 is a cyclic group of order 4. And 4 order cyclic group already I gave. What is that? 4 order cyclic group Z4. N order cyclic group is Zn always. Okay. So finally another 4 order cyclic group I am getting. So we can write direct hereafter u of 10 is isomorphism with Z4. This is cyclic. This is cyclic. Cardinality same and d order element same. Understood. So here we can write finally U10 is a cyclic group of order 4 with 2 generators, 3 and 7. Total number of generators also I gave. Generators are relatively prime elements. So total number of generators also phi of n in Zn. If Zn is a cyclic group, then generator is phi of n. Also I gave if G is a cyclic group of order n, then total number of generator will be phi of n. So here generator what will happen? Here already U10 cardinality is phi of 10 means 4. So total number of generator is 4. Sorry, phi of 4. So phi of 10. 2 times phi of will come here. Understanding? Right first. Finished. So like that we have to choose different U5, U6, U7, U8, U9, U10. If you will practice, if you will give time, then you can get different abelian group, non-abelian group, cyclic group, non-cyclic abelian group, everything you will get. Then we can write generalization. Another one question I will do, after this you can follow like this. Okay, direct generalization also mock-up don't do. Don't memorize. How I did everything openly. Like that, just element take, find Kelly table, abelian group, no need to verify. Inverse and all you can find. After that, direct you check it order of element. Because already we know that Zn star is abelian group, so Un is abelian group. Abelian group, no need to verify. Direct order of element find. If order of element and group order both are equal, this meaning generator will exist. So that is called a cyclic. Okay, we will see next another one. U of 8. 8 meaning 1, 3, 5, 7. Relatively prime element. Operation multiplication modulo 8. We will see this is cyclic or not. This is abelian must cyclic or not. Inverse element want we can find. 1 inverse will be 1. 3 inverse what will come? Itself will come. Because 3 into 3, 9 modulo 8, 1. 5 inverse, 5 will come. Means 5 into 5, 25, modulo 9, modulo 8, 1. All are itself coming. 7, 7, 49, modulo 8, 1. Itself inverse. And itself inverse meaning all are two order element. Okay. So here no need to find order. Also direct we can write U of 8 contains self-inverse elements with identity. Identity also self-inverse, but also particular right. So all non-identity elements, direct right U of 8 contains only two order elements with identity. So this is not cyclic. Only two order element is not cyclic then. So we can write U of 8 is a finally non-cyclic abelian group. Of order phi of 8. Phi of 8 means 4. So like that any group we saw already. Only two order element containing 4 order abelian group. Yesterday we saw. We can write finally U of 8 is isomorphism with Z2 cross Z2. Yesterday saw no? Z2 cross Z2 only two order element containing. Okay. Like that, suppose I will do U prime, any prime I will choose, U5. U5 meaning all 1, 2, 3, 4. All are relatively prime element with 5. Operation multiplication modulo 5. Correct. Here after this is confirm have abelian group. Cyclic or not we have to verify. Cyclic means we need 4 order element. Correct. Because U5 elements are cardinality is 4. So 4 order element. So same inverse element we can find or we can see. If self inverse not have means also we can tell must cyclic will come. Correct. Because 4 order this is. No self inverse means 4 order element will come. Order of 1 will be 1. 2 power 1, 2. 4. 8. 8 means 3. Power 4, 16, 1. Coming only 2 is the generator. Order of 2 is 4. And 2 inverse I think 3 will come. Because 2 into 3, 6 modulo 5, 1. So we can write that 3 also generator. So order of 3 is 4. 4 is not a generator. Correct? Because 4 power 1, 4 will come. 4 power 2, 16. Modulo 5, 1. So order of 4 is 2. So here 2 and 3 is a generator. So finally we can write U5 generated by 2 and generated by 3. So finally we can write U5 is a cyclic group of order 4 with 2 generators. So finally we can write U5 is isomorphism with Z4. Correct. Because this is a 4 order cyclic group. 2 generators, isomorphism with Z4. Understood? Right. Some UN group I am writing name that under like that explanation give workout more do. Then I will give generalization later follow. Generalization coming after this type explanation only. Okay, just how type I did now by elements. Don't go by generalization. Just for understanding and strong will go your concept. By element, everything explain this and all. Work out this is. Okay, right. Let her do this and all. Homework. Next, I will give generalization. So UN group sometime cyclic also, not for all n. But when this is a cyclic group, then total number of generator will be phi of n, because UN is a cyclic group of order phi of n. So total number of generator, again one phi will come. So here I will write if UN means not for all n, sometime only. Right. And in this case, we can write this also. For some. Finished. So this generation coming by whatever workout I gave, you see every time you will see cyclic and abelian, non-cyclic abelian both coming. So when u of 2 power r form, if any group you are getting, then after some workout you can go by generalization z2 cross z2 power r minus 2, r is greater than equal to 2. Okay. R is equal to 2 if you will choose here. Then this group cyclic will come. If R is not equal to, means only greater than 2, then non-cyclic abelian. This is. Because this is always in the form of product. So always abelian group. But R equal to 2 means here 2 minus 2, 0 will go. 2 power 0 is 1. Z1 means Z2 cross Z1 means Z2 only. So that is a cyclic. But if R is not equal to 2, only greater than 2, then only abelian, not cyclic. Sometimes this generation also asking. Here this is always cyclic for all P, but except 2. Because X related to separate I am giving here. This is always cyclic, Zn form. You can write this is always cyclic. And this U of P is isomorphism. This also cyclic only for all prime. And UN is a multiplicative group. Multiplicative group meaning multiplicative group or multiplicative function. This meaning that if we will do prime factorization of n, then after that we can make separate multiplication form. U of this into U of this into U of this, like this. After that, this and all separate formula giving we can use. Sometime you will see direct U of mn form, multiplication form. Both are relatively prime. We can make right separate. This multiplication meaning external direct product. On exam hall, they will use this sign. Okay. Same U of m1, m2, m3, m4, more than one halves, all are relatively prime to each other. So we can write like this. Okay. So related, whatever workout gave, properly do. After that generalization, use on exam hall and all. Exam hall also they will ask total D order element, D order cyclic group. Suppose they will give you 100. They will tell 20 order cyclic group, total 20 order cyclic group in U100. How to find it? So whatever UN group they will ask, you find by isomorphism. You change. Yesterday related like that we discussed. So you change isomorphism group and you find from here and you tell about that. Okay. Now you see U10 we saw, correct? U10 we can solve like this also. 2 into 5 prime factorization. Both are relatively prime. You can write U of 2 into U of 5. And both are prime U of P. Hereafter I can write U of P is isomorphism Z P minus 1, Z P minus 1. Z4. So finally U of 10 is isomorphism with Z4. Okay. Next U of 8 we did. 8 means U of 2 cube. U of 2 power R I gave. Isomorphism with Z2 cross Z2 power R minus 2. R here 3 have. So 3 minus 2 is 1. Means Z2 cross Z2. I gave formula, no, just now. Next I did U5. U5 means direct isomorphism with Z5 minus 1, Z4. Understood? So whatever UN group they will tell, you find isomorphism groups, and after that you find everything. Cyclic group, abelian group, non-abelian group, whatever. Abelian only UN. D order element, everything. Suppose U100 or U20. 20 means 5 into 2 square, prime factorization. 5 U2 square. U5 means isomorphism with Z, P minus 1, Z4, and U2 power R is Z2 cross Z2 power R minus 2. So R is 2. So 2 minus 2, 0, 2 power 0. So Z4 cross Z2 cross Z1. So Z2 cross Z1 means direct Z2, right? 2 and 1 GCD is 1. So this is isomorphism with Z4 cross Z2. They will tell total 4 order element in U20. You find from here. Yesterday we did, What will exist here? 1 order, 2 order, 4 order. Here 1 order, 2 order. So for U20, 1 order, 2 order, 4 order. No other LCM. They will ask total 4 order cyclic group in U20. So total 4 order element by phi of 4. Suppose U100. U100 means 2 into 5 and whole square. We can write U2 square, U5 square. Formula use. Isomorphism with this U4, this is. U4 direct I'm writing here after isomorphism with Z2. Because Z2 cross Z2 power R minus 2, that is 0, power 1 Z1 only will come. So direct Z2. U of P power R. P power R means Z P power R minus P power R minus 1. (25 minus 5, 20). So U100 isomorphism with Z2 cross Z20. Here after you find from here 1 order, 2 order, 5 order, 4 order, 10 order, everything will come. They will ask total 10 order cyclic subgroup from on U100. You find total 10 order element by phi of 10. Understood? Whatever they will ask related UN, find isomorphism group, find from here everything, 1 order element, 2 order element, all D order element, find from here, total D order element, total D order cyclic group, everything we can tell. Like this coming, then this is abelian. Zn form coming, cyclic. So U100 is a non-cyclic abelian group. Cyclic means always Zn form, but this is product form. We can't write Zn form. So this is non-cyclic abelian. Understood? Right. and all find. Just isomorphism group, if possible, d order element also find. D order element, total d order element, and d order cyclic subgroup. Okay. Finished. Coming, no? Some extra workout giving, let her do. Okay. Okay. So just isomorphism group find and find after the T order, D order element, which D order element, D order cyclic group, everything. Understanding? ZP cross ZP cross ZP anything. I gave yesterday Z2 cross Z2, Z3 cross Z3 cross Z3. So like that, any prime, if you will see, no, there only p order element will exist and identity. So one order element is only one. So total p order element is p power n minus 1. Whatever element have, all are p order element, all are except identity. So ZP cross ZP cross ZP cardinality is p power n. So total p order element is p power n minus 1. Minus 1 is that identity. Identity is a one order element, so minus 1. Okay. More time you will see in future, we are getting some group, that group only containing p order element. Any prime. Only containing 2 order element, only containing 3 order element, except identity. So that case we will see cardinality and we will decide this is isomorphism with Z3 cross Z3 or Z3 cross Z3 cross Z3, like this. So depend on cardinality, we can decide the G star is isomorphism with ZP cross ZP cross ZP cross dot 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 going on. Finite group. Here finite group, right? Finished. We will see new group hereafter. Klien group or Klien subgroup also telling, sometime K4 group writing, K4 subgroup writing. So Klien group is denoted by K4 and this is also symmetric group. Why? Because this is symmetries of irregular polygon 4 side, means rectangle. Symmetric group meaning same type of structure. Before that symmetric group we saw dihedral group. Dihedral group is the symmetries of square, 4 side, 4 regular polygon. This is the 4 side irregular polygon and irregular polygon means rectangle. 4 side. Okay. Other also 4 side irregular polygon have, but this group prepared by rectangle. And yesterday we saw permutation group, no, that is also called symmetric group. That is the symmetries of 1, 1, 1, 2 maps. Yesterday I wrote like this. I wrote symmetries word. Right, see in definition. Otherwise write any place. Sn is a symmetric group. Not writing, no. Any place write Sn means permutation group Sn. Permutation group Sn is a symmetric group. Any place, just for notation, no problem. Okay. Symmetries means same type of structure. In SN group, we are seeing 1 1 on 2 maps. So same 1 1 on 2 we are only. So symmetric group. Dihedral group, symmetries of 4 regular polygon. 4 side. That is a square. Square only, no? 4 side. Huh. 4 side irregular polygon more have, but this group prepared by rectangle. So especially I am rectangle also writing. So anyhow, K4 is a symmetric group. So next we will see what is the element of K4. So rectangle, one rectangle we will choose, and we will see that how many symmetric rectangle we can make. Suppose 1, 2, 3, 4. So this is the same position, means just you think 0-degree position. So 0-degree position we will write in the element form. So 1 maps to 1, 2 maps to 2, 3 maps to 3, 4 maps to 4. Two type of notation giving. Element form and rotation reflection form. So this is identity. Hereafter, this rectangle again same type structure when will come? How type rotation we will give? 90-degree rotation will give me this type will come. That is not the same. Same means like this position again will come and complete 180-degree rotation we will give. This is the rotation. Complete 180-degree. Okay. This meaning 1 maps to 3, 3 maps to 1, 2 maps to 4, 4 maps to 2. This is name is 180-degree rotation. By mapping, we can write like this: 1 maps to 3, 3 maps to 1, 2 maps to 4, 4 maps to 2. Okay. Again, we can get same rectangle. Here after rotation not possible. Again rotation will give me again 0-degree position will come. Correct? R360 degree. So only in rectangle two type of rotations. Next we can do reflections. Horizontal, vertical. So first horizontal we will do like this. So here will come 1 maps to 2, 2 maps to 1, 3 maps to 4, 4 maps to 3. 1 maps to 2, 2 maps to 1, 3 maps to 4, 4 maps to 3. Next we will do vertical. V means in 0-degree position like this. So 1 maps to 4, 4 maps to 1, 2 maps to 3, 3 maps to 2. 1 maps to 4, 4 maps to 1, 2 maps to 3, 3 maps to 2. Hereafter, not possible. Rectangle, 2 rotations, 2 reflections only possible. No other symmetric curve. Okay, so finally K4 elements are two type notation can give. First notation is R0, R180, H and V. Another notation we can give identity 1324, 1234 and 1423. You see all are product of transposition. All are even permutation. 2 order element. This is 2 order element, 2 order element, 2 order element. Okay? Right first, then I will explain next. K4 elements, two type of notation I gave. R0, R180, HV, and another one SN element. But can I write K4 is a subset of D4? Can write? Can't write. D4 is a group of regular polygon, but K4 is a irregular polygon. Notations are same name, R0, R180 there also, but this notation approach is different. There are R180 degree rotation in rectangle. There are R180 rotations in square. So by element you don't tell subset. Both are different group. Okay. For that especially we can't write. This type don't write. But we can write K4 is a subset of S4. Because K4 elements are subset 2 order element in S4. Also we can write subset of A4. A4. Even permutation no other. So 2 order even permutation in A4 is 3. 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. This only. Okay. And here after K4 is a group or not. K4 is a first class group. You can see that K4 containing only 2 order element with identity. All are 2 order element. We can write here K4 contains only 2 order element. With identity. So just now I told any group is containing only p order element with identity. We can write this is isomorphism with Z2 cross Z2, Zp cross Zp. 4 order, no? K4 contain only 2 order. What is the cardinality of K4? 4. So this is isomorphism with Z2 cross Z2. Okay. So anyhow, finally we can write K4 is a non-cyclic. This is not a cyclic, non-cyclic abelian group. Of order 4. I forget to write your name, no? I wrote, no, or not, I wrote. Sometime, some basic book, university book and all, they will write A, B name, K4 elements and all. I don't know you are BSc, MSc or not. A, B, they will write. What is the meaning of this? R0 have, R180 have, H have and V have. R180 is this. HV multiplication you will do, no, R180 will come. Means just you think, this is what name I gave. First is R0. This is R180. This is R180. So, and this is H and this is V. Correct? So just one thing you do. Identity where have no, there next another name give like this notation E. And H name you give A, and V name you give B, and this R180 name you give HB, means AB. This composite function operation you will do now, this will come. You see, I will do. HV, AB, 1, 2, 3, 4, B is 1, 4, 2, 3. So two permutation have, we have to operate. 1, 2, 3, 4 means 1 maps to 2, 2 maps to 1, 3 maps to 4, 4 maps to 3. This can write direct. Yesterday I told, no need to do separate. Because disjoint permutation we can't merge. So direct write. Again 1, 2, 3, 4. 1 maps to 4, 4 maps to 1, 2 maps to 3, 3 maps to 2. Here after map to like this. 1 maps to 4, 4 maps to 3, 1 maps to 3, 2 maps to 3, 3 maps to 4, 2 maps to 4, 3 maps to 2, 2 maps to 1, 3 maps to 1, 4 maps to 1, 1 maps to 2, 4 maps to 2. So this is 1 maps to 3, 3 maps to 1, 2 maps to 4, 4 maps to 2. You see this is R180. Okay. So sometime K4 elements, they will write like this notation also. After this, no, you write K4 notation, new type. K4 we can give like this notation also. Identity A, B, A, B. What is A, B? Here writing have. Okay, write first. So finally K4 elements A, B, AB type have. That is the notation. AB means HB. And K4 is a group hereafter. So K4 is a subset of S4. K4 is a subset of A4 and a subgroup group. So we can tell K4 is a subgroup of S4 also, subgroup of A4 also. Final. For this region, no, this group is a subgroup of two groups. For this region, no, this group telling Klien subgroup also. That is the reason. This is group as well as subgroup. Okay. So from K4 we can get only two order elements have. So two order subgroup and one order subgroup. Two order three element have. So two order three subgroup. And itself, last subgroup is itself. Okay. And this all subgroups are cyclic subgroups we can tell. One order. This is two order cyclic subgroup. This is also two order. This is non-cyclic already. I told no four order element. Right. Finish. Hereafter we will see Cosset's and Lagrange's theorem. Oh, set means partition. Means hereafter we have group, we have here set means group with a sub G star. So that group we will do partition. And partition we will do by the help of subgroup. Coset, just you think here H is a subgroup of G. H is the just measurement we need. We have G is a group. Suppose finite group have 10 order group have, and that 10 order group correctly partition we have to do. So what is the possible order of subgroup? By subgroups only we have to do partitions. So possible order. Suppose you have 10 centimeter bread. Correctly partition have to do. Correct size. Every piece size will be correct. So what is the possible size? Suppose 10 centimeter bread have 1 centimeter. If I will do partition, how many piece will come? 10 piece correctly will come. 2 centimeter, then how many piece? 5 piece. 3 centimeter, then 3 centimeter partition. If every size I want 3 centimeter, then what is how many pieces remaining will come? Means that is not a correct size. So 3 centimeter is not perfect size. Height will come. Suppose you are 4 person. 3 centimeter partition will do. You will get correct size this 3 person. Matthew will get last little size, that is 1 centimeter. He will fight, no? Correct fight will come. I don't want. Sir is partiality doing. Sir is not good person. They are correctly giving for me only living. Height will come. So this meaning 3 centimeter is not correct size for that bread. So what is correct size? 1 centimeter, 2 centimeter, 5 centimeter also correct size. 5 centimeter means 2 piece, and itself 10 centimeter, 1 piece. So 10 order group have. So subgroup cardinality possibility what? 1 order, 2 order, 5 order, 10 order. Means divisors of 10. This only from starting we are doing. We saw no 10 order group. What is the divisor? D order element, that only D order subgroup. So subgroup is the possible divisor will be the subgroup order always. Otherwise tension, fight, everything will come. Okay. So here whatever infinite group is different, that is different, you leave it. Infinite group also subgroup we can find, that is different. But I'm telling our G is a group means just our complete you think bread, and H is the subgroup of G means that is correct size of pieces. So depend on H we can decide how many pieces will come. Okay. So here have left coset, right coset. Means have to from right side have to cut, from left side have to cut. Suppose you have bread, you will start cutting from right side, or you will start from cutting from left side. Any side cut, same size will come, same pieces will come. If 10 centimeter have bread, if 2 centimeter partition if you will do, every piece size is 2 centimeter, 5 piece only will come. Either you cut from right side or cut from left side. Correct. So that is called a left coset and right coset. Understanding? So left coset, right coset definition I am writing. After that we will see that how many distinct left coset, right coset will come. So just divide 10 centimeter. If 2 centimeter partition we need, so 5 coset, 5 piece, 5 coset. If 1 centimeter, then 10 cosets, 10 partition, 10 coset. Understood? So first I will write left coset, right coset definition. Here AH means star, huh? Whatever group, AH means not a multiplication, whatever group operation here will come. Okay, sometime like this also giving A star H, H star A. Means from right side operation have to do, left side here also star. Whatever operation here will come. Finished. So first we have to choose any group, either finite or infinite group, anything. After that we will choose subgroup of G star. After that, by the help of subgroup, we will find left coset, right coset. Both we will find. For all A belongs to G, whatever A have in G, with H operation we will do one by one, and left side, right side, both we will find. So this is called a left coset, this is called a right coset. Means whatever H element have, in H element we will choose one by one A from G, and from right side and from left side we will do operate. Whatever operation have. And we will see left coset, right coset, whatever came. And after that we will verify how many distinct left coset coming, how many distinct right cosets coming. That only here writing. If two distinct I am writing, distinct with distinct, completely intersection 5 will happen. Otherwise both are equal. No anything common will come. Okay. So these two distinct cosets are either disjoint or identical. Identical means no distinct, same. We can't tell that at least one element common coming, nothing common will come, distinct means. Okay. So just now I told coset is the partition. Either left coset find or right coset find. When this is a partition, this meaning union I will choose, then G will come. Or cardinality addition I will do, then G cardinality equal will come. Okay. H is a subgroup. So whatever H cardinality have, left coset cardinality, right coset cardinality, everything same. If this is a 10 order group, then left coset, right coset, 10 order subgroup will come. Means 10 order cardinality. Cosets are not a group or subgroup, anything. E, if we will operate either from left side or right side, H only will come. Hereafter, definition of index of subgroup. Index meaning total distinct left coset, right coset. Okay. Suppose 10 order group have a subgroup order is 2, then 5 pieces will come, no? This meaning 5 distinct left coset, 5 distinct right coset will come. Okay. That is called an index. So here notation I have to give. So index of subgroup notation is this, and this meaning total distinct left coset, right coset. Suppose this is just common I gave definition. Suppose our G star is a finite group. Finite group case, infinite group not. Finite group case, index is equal to, can I write that order of G by order of H? This only work we are doing, no? 10 centimeter bread have, subgroup cardinality is 2 have, then 10 divide 2 divide 10, 5. 5 pieces is there. Huh? 2 divide 10, 5 only. So 5 pieces. So 5 distinct left coset, right coset. Finite case. Infinite case we can't divide, you know. There we have to, infinite case also finite possible, finite number of cosets. But by divide we can't go. Correct? Right. And this only Lagrange's theorem. If H is a subgroup of finite group G, then order of H divides order of G. This is called Lagrange's. that only here again I will prove. I explained by bread example, and here by coset I have to prove. We have G star is a finite group. And H star is a subgroup. So when subgroup have, then left coset, right coset we can find. So just suppose that let we have R distinct left cosets. Anything, right? Yourselves can choose. Left cosets of H in G. This left coset means these are our pieces. Piece 1, piece 2, piece 3, piece 4 from left. Okay. So when left coset we saw, then we can write G is equal to this coset is partition. So we can write like this. And just now I told when this equal, cardinality is also same addition. And just now I told AH cardinality and means right coset cardinality, left coset cardinality, subgroup cardinality, everything will be same. Rth times. So cardinality of G, Rth times addition will do means like this only will come. So finally cardinality of G by cardinality of H is equal to R. And when finally R coming, this meaning we can divide. So theorem here proved. Cardinality of H divides cardinality of G. Theorem proved. But by this theorem, this only before I told that cardinality of G by cardinality of H is equal to R. And what is this? Index of subgroup. Understood. So by braid concepts we proved. Now we that braid pieces name A1, A2, A2H given and proved. Concept is same. Understood. Right. Finished. Hereafter, just one example I will do how to find cosets. After that, your work. Lunch time, no. Left coset, right coset, find. Minimum D3 and D4. Because these two we will use every places. Remaining not doing also no problem. But D3, D4, if you will do, then we can proceed more concepts. Otherwise, I can't do hereafter. Only for knowledge I am telling. Won't ask on exam hall. Only for knowledge. I will write also some concepts. If that work, if you will finish means you can understand it easy way. Otherwise, you will think, okay, sir told me this will happen like this. Okay. So how to find, you see. Whenever left coset, right coset, if you will find, if your group is abelian group have, then both will be same. So anyone find. If non-abelian group have, then both you find for every subgroup, because some subgroup left coset, right coset will be equal, not for every subgroup. But if G star abelian group have, then for every subgroup, left coset, right coset will be equal. That one time write first. Another one thing here, sometime on exam hall, converse of Lagrange's theorem, true or not, they will ask. Converse of Lagrange's theorem means if order of H divides order of G, then H is a subgroup of G or not. So converse of Lagrange's theorem is true only for finite abelian group. We saw some infinite, some non-abelian group we saw. Converse is not true. Just like A4. A4 cardinality 12 have. But in A4, 12 divisor what will come? 1, 2, 4, 6, 12. 6 order subgroup not possible there. Because in A4, 1 order, 4 order subgroup will be there, 12 order subgroup will be there, 3 order subgroup will be there, but 6 order subgroup not possible. A4 element I gave no yesterday. 1 order element existing, 2 order element existing, that product of transposition, and 3 order element existing. 4 orders that cycle not existing, 4 cycle, that is odd permutation. But 4 order subgroup will be K4. Identity 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. That will be the subgroup of A4. So 4 order subgroup will exist. 6 order subgroup does not exist. Here you write one time as 4 element find must, then you can understand this 1, 2, 3, 4, 1, 3, 2, 4 how coming. Only night, evening reaching 6:30, 7:30, after the sleeping, wake up 5 o'clock, that is not possible. Converse of Lagrange's theorem is true only for finite abelian group. Finite abelian group only. Converse is not true for finite non-abelian group, because contradiction have. Non-abelian also true, but contradiction have. So statement true we can't tell. But not true for finite non-abelian group. Contradiction, our contradiction will be A4. A4 cardinality is 12. What is the divisors? 1, 2, 3, 4, 6, 12. 1 order subgroup will exist, identity. 2 order subgroup will exist. 2 order element have no. All 2 order element I think 3 have. So 3 subgroup will exist. 3 order subgroup will exist. 3 order total element maybe 8 will come. By formula you can yesterday did. So subgroup will exist. 4 order subgroup will be K4. The 2 order element will come. 4 order element not existing in K4. Because that 4 cycle is an odd permutation. So no 4 order element. But 4 order subgroup is there. 4 order subgroup is K4. That identity and 2 order all element, 3 elements. 6 order subgroup not possible here. 12 order subgroup itself is there. No 6 order subgroups. If you are thinking how, then you go by elements. Already elements you find as per element you find first. A4 element find. After that you can see 6 order, no any subgroup will come. We can't make 6 order subgroup by 2 order and 3 order. Sometimes 6 order subgroup we can make by 2 order element and 3 order element. But here not possible. Okay. So here I am writing 6 divides 12, but 6 order subgroup does not exist in A4. This handle mug-up don't do, huh? Little you find S4 element in home. Time give S4 element find, A4 find, and after that you verify. You can find it. When we have elements, then we can find all subgroups. We don't need any theorem or formula. Okay. At least A4 subgroups and I'll find. Because A4 cardinality is 12. Yeah, factorial 4 by 2. So 12 will come. So 12 elements is easy only. By 12 elements subgroup find. As per subgroups you will feel tough. More elements are there. But A4 subgroups you can find. Only 12 elements have. And elements have means subgroups is easy. You can try. Huh? Try later. You see 6 order subgroup you can't find. Understanding G when abelian group have, then for all subgroup left coset right coset equal. When non-abelian group have, then for some subgroup only will be equal. Some subgroup not equal. Anyhow, if G star abelian group have, then anyone find. Either left coset find or right coset find. Both no need to find. But when non-abelian group have, then for every subgroup, you have to find left coset, right coset both. Either equal or not equal. Okay. Suppose that 6 I choose. Here we have 1 order, 2 order, 3 order, 6 order subgroup. Suppose I will choose 2 order subgroup. Order of H is 2. What is that subgroup 2 order? 0 and 3. And hereafter this is abelian group, so anyone left coset, right coset, anything we can find. Both are equal. So hereafter for all A belongs to Z6, I will find left coset. This meaning operation here addition modulo 6. And A plus H meaning we have to add with every element. For all H belongs to H. This is the meaning from left side or from right side. So try. Suppose I will choose 0. For all I have, so 0 plus H. So 0 plus H, same element will come. 0 plus 0, 0 plus 3. Next 1 plus H. 1 and 4 will come. Next 2 plus H. 2, 5 will come. 3 plus H. 3, 3, 3, 6. Modulo 6, 0. See here, hereafter repetition will come. 3 only distinct will come. You see 3 plus H coming 0, 3. 0, 3 means this. So 3 plus H meaning 0 plus H. Next 4 plus H. 4 plus H means 4 plus 0, 4. 4, 3, 7. Modulo 6, 1. You see 1, 4. 1, 4 is this. So 4 plus H is equal to 1 plus H. Next 5 plus H. 5 plus H means 5 and 8. Modulo 6, 2 means 2, 5. So 2, 5 is this 2 plus H. Understood? So how many distinct left coset coming? 3. 0 plus H, 1 plus H, 2 plus H. Three distinct left cosets of H in Z6. You see all union, you see Z6 will come. All are partition. And here abelian group, so left coset, right coset both are equal. So separate, no need to find. Understood? So group order is 6. Subgroup order is 2. So 6 by 2 means 3. 2 divided 6 is 3. So 3 coset. Suppose 3 order we will choose. Suppose I choose next again. I choose H1 name I am giving. H1 order I am choosing 3 order subgroup. 3 order subgroup who is here? 0, 2, 4. 3 order subgroup means 2 distinct left coset will come. 6 by 3. 2. So 0 plus H1 will come. 0 plus H1 means same 0, 2, 4. 1 plus H1. 1, 3, 5. You see here after repetition will happen. 2 plus H. 2 plus H means 2, 4, 6. 6 means modulo 6, 0. You see 0, 2, 4. 0 plus H1. 3 plus h1 is equal to 1 plus h1. 4 plus h1 is equal to 0 plus h1. Again 5 plus h1 is equal to 1 plus h1. Repetition. Okay. Means 3 plus h1 if you will find, this will come 1 plus h1. 4 plus h1 if you will find, this will come 0 plus h1. Again 5 plus h1 if you will find, again 1 plus h1. Means anyhow only two distinct left coset, right coset. 0 plus h1, 1 plus h1. Understood? So this is Z6, operation is addition modulo 6. So from left side, right side, addition only have to do under modulo 6. If suppose Z8 you will choose, then under addition modulo 8. Suppose D3, D4 we are going. D3, D4 operation is composite function. So composite function we have to apply from right side, left side. Understand? So I will tell this you write and D3 and D4. Now how much can do? At least D3 finish, homework D4 finish. So just you think D3 have whatever subgroup. You can leave it one order and itself. One order subgroup I will choose means total 6 pieces will come here. So one order and itself leave it. Whatever subgroup have 2 order, 4 order, that subgroups and all left coset, right coset both find for D3 and D4. Okay. Write this.